What if I told you that one of the most powerful revolutions in physics began with a question so small it almost sounded meaningless? Not about stars, not about black holes, not even about atoms, but about a single electron, a particle so tiny that trillions of them can pass through your body every second without you ever noticing. And yet, hidden inside that particle is an answer that reshaped our understanding of reality itself. This is not just a story about numbers or equations. It is a story about curiosity, about how human beings dared to measure the immeasurable and question the invisible. When scientists asked how heavy an electron is, they were not simply chasing a value. They were challenging the limits of knowledge, precision, and imagination. What followed was an experiment so elegant and so profound that it changed the way we think about matter, energy, and the universe. As this journey unfolds, you'll discover how something unimaginably small can control the size of atoms, the stability of matter, and the technology that powers our modern world. Stay with this story until the very end, because the deeper we go, the more you'll realize that the smallest questions often carry the greatest power to change everything we believe about the universe. The electron appears simple because it is often introduced as just a tiny particle with negative charge, but this simplicity is deceptive. At first glance, the electron seems like a basic building block of matter, something that can be neatly placed inside atoms and treated as a point-like object. However, when physicists began to study it closely, they discovered that the electron does not behave like any familiar object from everyday life. It can act like a particle in one experiment and like a wave in another, spreading out through space and interfering with itself. This dual behavior challenged classical physics and forced scientists to rethink what it even means for something to exist in a definite place. The deeper meaning of the electron becomes clearer when its role in the structure of matter is considered. The size of atoms, the stability of matter, and the formation of chemical bonds all depend on the properties of electrons. Without their specific behavior, atoms would either collapse or fail to hold together. The electrons' interactions reveal that nature at the smallest scale is governed by probabilities rather than certainties, where outcomes can only be predicted statistically. What makes the electron especially profound is that it connects multiple fundamental ideas in physics. Its behavior is explained using quantum mechanics. Its motion and energy relate to relativity, and its interactions underpin electromagnetism. Through the electron, abstract equations turn into physical reality, showing that even the simplest looking particle can carry deep insights about how the universe truly operates. Mass at the quantum level cannot be understood in the same way we understand mass in everyday life. In the macroscopic world, mass is measured by placing an object on a scale and observing how strongly gravity pulls on it. This method completely fails when dealing with particles like electrons because they are far too small to be weighed directly. Instead, physicists must infer mass from how a particle behaves when forces act upon it, especially electric and magnetic fields. At the quantum scale, mass reveals itself through motion, resistance to acceleration, and changes in energy rather than through direct measurement. The challenge becomes even deeper because quantum particles do not follow smooth, predictable paths. An electron does not travel like a tiny billiard ball. It exists as a probability distribution, spread across space until measured. This means its mass cannot be separated from its quantum behavior. The mass influences how sharply the electron's wave function spreads, how tightly it can be confined within an atom, and how it responds to external fields. A lighter particle behaves more like a wave, while a heavier one behaves more like a localized object. What makes quantum mass especially significant is its connection to energy. According to modern physics, Mass and energy are interchangeable, and, at small scales, this relationship becomes unavoidable. Even slight changes in energy can alter how a particle behaves, making mass a dynamic property rather than a fixed label, and in this way, measuring mass at the quantum level becomes a window into the deeper structure of reality, where familiar concepts are transformed into something far more subtle and fundamental. The historic experiment that revealed the electron's mass marked a turning point in the development of modern physics. Before this breakthrough, electrons were known to carry electric charge, but their mass was uncertain and deeply debated. Scientists could observe electrical effects, yet they lacked a clear understanding of how heavy these particles actually were. The experiment approached the problem indirectly, using carefully controlled electric and magnetic fields to study how electrons moved under known forces. By analyzing the curvature of their paths and the way they accelerated, physicists could relate motion to force and extract the ratio of charge to mass with remarkable precision. This approach was revolutionary because it replaced direct measurement with inference based on physical laws. The results demonstrated that electrons were far lighter than even the smallest atoms, proving that matter was divisible into components far more fundamental than previously imagined. This discovery forced a radical shift in atomic theory, transforming atoms from indivisible units into complex systems built from smaller particles. It also provided a quantitative foundation for future theories, allowing predictions to be tested with mathematical accuracy rather than philosophical speculation. The impact of this experiment extended far beyond a single number. It validated the use of fields as powerful tools for probing the invisible world, and showed that unseen particles could be studied through their effects on measurable quantities. By revealing the electron's mass, the experiment reshaped scientific thinking, laying the groundwork for quantum mechanics, solid-state physics, and modern technology, and establishing precision experimentation as a cornerstone of physical discovery. Precision measurement transformed physics by shifting it from a largely qualitative science into a deeply quantitative one. Before such measurements were possible, many theories relied on broad assumptions and approximate reasoning, which limited how confidently scientists could describe the behavior of nature at small scales. When experiments became precise enough to detect tiny deflections, minute time delays, and subtle energy changes, physics entered a new era where ideas could be tested with extraordinary accuracy. Measuring the electron's properties was a defining example of this shift, because it required instruments sensitive enough to respond to effects that were previously invisible. Through precision, abstract concepts gained physical meaning. Small discrepancies between predicted and observed values exposed weaknesses in existing theories and pushed scientists to refine or replace them. In the case of electron measurements, the results confirmed that classical mechanics alone was insufficient, opening the door to quantum explanations. Accuracy turned experiments into conversations with nature, where even slight deviations carried deep significance. This emphasis on precision also reshaped scientific methodology. Experiments were no longer just demonstrations. They became rigorous tests capable of validating or falsifying entire theoretical frameworks. Reproducibility, error analysis, and controlled conditions became essential elements of discovery. As a result, physics gained a new level of reliability and predictive power. Beyond theory, precision measurement laid the foundation for technological progress. The same techniques developed to measure electrons led to advances in electronics, imaging, and communication systems. By demanding exactness, physicists learned that understanding the universe depends not on grand gestures, but on careful attention to the smallest details. Where the true laws of nature quietly reveal themselves, the electron's mass plays a crucial role in connecting quantum mechanics with relativity. Two pillars of modern physics that describe reality in very different ways. In quantum mechanics, the electron is treated as a wave particle whose behavior is governed by probabilities and energy levels. Its mass determines how its wave function spreads, how tightly it can be confined within an atom, and how it occupies discrete energy states. Without the correct value of mass, the mathematical structure of quantum theory would fail to match experimental observations, and atomic stability would remain unexplained. At the same time, relativity reveals that mass is not an isolated property, but is deeply linked to energy and motion. Even for an electron moving at high speeds, relativistic effects begin to appear, altering its effective mass and behavior. This becomes especially important in high-energy experiments and particle accelerators, where electrons approach the speed of light and classical assumptions break down. The electron's mass sets the scale at which these relativistic corrections become significant, ensuring consistency between theory and observation. What makes this connection profound is that the electron exists at the crossroads of these two theories. Its mass allows physicists to test where quantum mechanics must be adjusted, to respect relativistic principles leading to more complete frameworks that describe particles and fields together. Through the electron, mass becomes a bridge rather than a boundary, showing that the deepest laws of nature are unified. This tiny particle demonstrates that understanding reality requires blending quantum uncertainty with relativistic precision into a coherent picture of the universe. Tiny particles have the power to redefine the laws that govern the universe because they reveal the fundamental rules hidden beneath everyday experience. Large objects follow patterns that feel intuitive, but at the smallest scales those intuitions collapse. Particles like electrons expose behaviors that seem strange, yet these behaviors are the foundation upon which all matter is built. By studying something so small, physicists are forced to confront principles that apply everywhere, even if their effects are only noticeable at microscopic levels. The electron is a perfect example of how scale does not limit significance. Its properties determine the structure of atoms, the nature of chemical reactions, and the flow of electricity. A minute change in its behavior would alter the stability of matter itself. When experiments uncovered the electron's true characteristics, long-standing assumptions about motion, energy, and causality had to be revised. Concepts such as certainty, locality, and determinism were replaced by probability and statistical laws, reshaping the philosophical foundations of science. What makes tiny particles so influential is that they act as testing grounds for universal theories. Any law that claims to describe nature must also explain the behavior of its smallest components. When discrepancies appear at that level, entire theoretical frameworks can be challenged or discarded. This is how revolutions in physics begin, not with massive forces, but with subtle inconsistencies in small-scale behavior. Through particles like electrons, physicists learn that the universe is governed by principles that operate quietly and precisely. These tiny entities remind us that the deepest truths of reality are often written in the smallest letters of nature. As we bring this journey to an end, one truth stands out clearly. Asking how heavy an electron is was never a small or trivial question. It was a doorway into a deeper understanding of reality itself. Through careful experiments and extraordinary precision, a particle once thought to be simple revealed layers of complexity that reshaped atomic theory, transformed measurement, and united ideas from quantum mechanics and relativity. The electron showed us that the universe does not yield its secrets easily. But when it does, those secrets change everything we think we know about matter, energy, and existence. By studying the tiniest components of nature, physics learned how powerful curiosity can be and how even the smallest discoveries can echo across the entire cosmos. Good luck on your journey of learning and exploration. May curiosity always guide your questions and courage push you to seek deeper understanding. Thank you for your time, your attention, and your passion for discovering how this incredible universe truly works.